let's definitely get started. It's good to see some friendly faces here today, and it's our chance to do some review of the exam. Um, my hope for the exam is that there's no surprises on it, and certainly, hopefully, after today, there should be no surprises for you on Wednesday. But having said that, every semester there tends to be some who are surprised by what the exam turns out to be. So I'm trying to fix that for this semester. So there should be no surprises, is my hope at least. This content is up on Canvas for the week 5 module, as well as basically a previous semester's exam. So I called it sample exam questions. Worked on that with another professor in the department, but basically it's a copy of a previous semester's exam. It's going to look a little different this time around because I am attempting to put everything in a canvassy kind of way versus just uploading a PDF. So some of the questions got kind of canvassized, turned into fill in the blank or multiple choice, but the content and the length is roughly very comparable to that example you can see on Canvas. If we have time, we can also look at that example directly if time allows, or we can do that in office hours or otherwise. Um, so this is the big takeaway from today. If you remember nothing else, this is all I want you to remember from today. And I mentioned before we started recording, I have when you're a student, you maybe have that recurring nightmare where like you forgot to wake up and go to an exam. I don't know if any of you have ever had that dream or kind of nightmare. And the weird thing is, at least for me, is it never goes away. I still occasionally have that dream where I overslept and missed an exam, and I'm really stressed out. And then I wake up and say, "Well, but it's okay. Wait, I'm the instructor. If I overslept an exam, it'd be bad, but we'd be okay. We'd find a way to work things out." But this Wednesday, please don't oversleep. Please come to class. Please join our Zoom session as if it were a normal lecture on Wednesday. It'll be proctored like we've been proctoring our quizzes, and effectively this exam is 6 or 7 quizzes back to back is basically what this exam structure is going to be. So I'm planning to schedule it for that 50-minute time window we have together. It is completely open in terms of open book and open notes, but I'll talk about that in just a second here. It is, and I've said this enough times now. It's not collaborative. Um, I don't have the safe browser feature turned on or any of those things that like tracks your eye movements or your EKG or anything like that to determine if you're cheating or not. But I'm trusting you and to be honest to yourself and to your peers. I, as I've been putting together the exam, it's not that clear you could really cheat on it if you wanted to anyway. Like, what is cheating in this context of an open book, open note exam? But my assumption is that your work is your own. So it's whatever you put down. If it's a short answer question, that's your work. That's your thoughts. To me, if as long as you've done that, then you're fine. I have no concerns about cheating, and I'm not too worried about it for this. If it was a take home, maybe I would be more worried about it. So, but my suggested strategy, if this was an in-person exam, I would have made this somewhat more mandatory, would be to actually, as you prepare between now and Wednesday, make 1 or 2, and probably no more than 2, pages of notes to have handy to reference during the exam. Being open notes is kind of a blessing and a curse, to be honest. Um, there's just too much content, right? And the way I've timed out the exam in terms of the number and the style of questions, if you get a question, you say, "Well, let me see where in the textbook it talks about this subject matter." You may get that question complete, but you're going to run out of time on the exam because you'd be treating it a little bit more like a homework assignment than you'd be treating it like an exam. But it is useful to make that relatively short, in exam kind of cheat sheet of here are the key concepts I thought were most important. You can really distill down this first 5 weeks of the semester into just one sheet of paper pretty easily, and I just recommend that so that you have that to reference to. Yes, it's open book. I don't think it's a good strategy to ever have to actually look into the book for this, and that's the point I was trying to make here. A couple questions already about the green sheet or green card. Yeah, absolutely. And in fact, if we were to look at the exam itself, um, I even linked to it in case you can't find it handy. It's there. But my suggestion for that is that's a very information dense sheet of paper, that MIPS green card, right? It's a little hard. You have to almost translate it from MIPS shorthand into English, right, to be able to answer a question based on what's on that green card. So you definitely don't want the exam to be the first time you ever look at the MIP screen card and understand it. You also won't have time to say, oh, what are these footnotes here? What does this mean here? What is this column here? Where does it show the opcodes in the green sheet? You should be familiar with it before Wednesday, and then it can be a very great reference for you on Wednesday. But if it's really the first time you've looked at it, you're going to have kind of a tough time. And same with Mars. Mars is also wonderful. We always talk about how Mars is kind of the if there's some ambiguity between what I say and what the textbook says, well, what Mars says is the answer to the question because that's what our code has to work on ultimately in this class. But you probably will have um, gonna have a bad time if like you're trying to open up Mars and see if this assembly sequence works. The questions I believe I've put together should not require you to ever have Mars open to ever run anything. There is some MIPS short answer questions, um, but how I would grade them would not be based on me loading it up into Mars and checking that things run perfectly. It's sort of an eyeball test. Yeah, this student, as they provided this MIPS answer, knows what they're talking about. I don't care about the really low level syntactical details of did they use an add or an add you instruction for this thing. That kind of thing doesn't really matter to me, and so it won't matter on the exam either. In terms of the exam focus, when I say there's no surprises on the exam, that's kind of what I meant in terms of what content is being covered. We've basically had 4 weeks together. We've had some fun, we've had some laughs, some tears along the way, but it's been 4 weeks, and there's been these two separate segments of the class. There's been the things we've been covering together, which have been best encapsulated by homework questions, reading, lecture notes and our discussions during actual lecture itself. And then there's been this whole painful, lab experience. This exam will be covering in-class things. They'll be covering lecture 1 through 4, homework 1 through 4. It is not covering the lab experience. I'd mentioned that before. I just want to reiterate that here. There are no VHDL questions. There are no VHDL adjacent type questions. There's no model sim questions. We could have done that, but you're getting enough points this semester for struggling with model sim and VHDL. There are questions that are about the relationship between ISA and microarchitecture because we have been talking about that a lot. How would you implement such a thing? And again, as sort of a short answer question, you won't be able to draw a schematic. You won't be able to implement it or being asked to implement it in VHDL. But do you have a general understanding of what the register file is doing? So to me, that's not a lab question because we've been covering it a lot in class as well. We've been drawing it out. We've been discussing the architectural implications of some of the ISA design decisions we've had there. And and these are the main topics that we've covered, right? The ISA architecture, a little bit of the register conventions, and we've just been doing a lot of translation of functionality down to MIPS. What does the MIPS provide for that functionality? How do we go from either C-like syntax or maybe pseudo MIPS or pseudo assembler MIPS syntax down to native MIPS instructions? Basically, how do we implement stuff in MIPS? And there's gonna be a lot of questions, both conceptual as well as you can call them programming questions, but they're really programming short answer questions. There are no questions that are deliver this long program and prove that it's correct. That's more of a homework question. You've had good experience. That should get you ready for the exam questions, but it won't be programming questions in that nature. You just wouldn't have time to do that in a timed exam like that, I would think. So in terms of the textbook, I have tried in terms of listing in the homework as well as listing in the beginning of lecture notes what sections of the textbook are associated with what we've been covering. And I think it's a pretty good textbook, at least these first couple of chapters. And that should be all you should really have to review if you want to review it. That good chunk of chapter 1, as well as the majority, really the entirety of chapter 2 that talks about the ISA. I mentioned the VHDL chapters here, but that's not needed for the exam. So this is what we've covered so far. We've made a lot of progress on the VHDL book as well, but it's the computer organization and design, um, basically the first 2 chapters of that. It's a good use of your time if you haven't done so yet to just read through them. Read through them, take notes, ask questions on Discord. If the book says something that doesn't make any sense, you probably already had to do a little bit of that to get through the first 4 homework assignments, or at least the 3 that you've gotten submitted so far. Um, But do it again if you haven't done so, and take notes and start to build, yeah, that sort of crib sheet of here are the big picture concepts that could make for good exam questions. So the green card is going to be provided. So you should know that at this point. You know it is exam time, so um, you don't want to come into the exam, thinking, well, I don't really know the MIPS instructions, but I can kind of wing it and I can kind of look it up on the exam, given the questions and the time that's available. Um, I expect you to know it's been about 17 instructions, I think, in total we've really covered now. We haven't really talked about a lot of the other ones. Um, and I would expect you to be pretty fluent in them at this point in the semester, or at least if not today, come Wednesday morning. I would expect that of everyone. The questions are timed, and the difficulty, I believe, is scaled for that student who knows MIPS, at least at that level at this point of the semester. Register usage conventions. The extent we did a very good job or not of covering that. There's now been a couple homework questions, and the textbook chapter 2.8 does talk about it. At the very least, I want everyone to appreciate stack management and the stack arithmetic that we spent a couple days on. The bookkeeping of the stack frames, as well as temporary versus saved registers, caller saved versus callee saved registers. There is a question definitely on there that expects you to be aware of what's happening with those. There is a little help to those who actually showed up today. There is no question that says uh, create this recursive function in MIPS and make sure you follow the procedure call interface. So I would say you don't have to be that fluent in it, but you have to be pretty aware of what's happening there. Um, those are some very simple problems. I have a listing. If we go past all the MIPS conventions, that's just from lecture 4. Um, and I'd mentioned this at the end of lecture 4 before we did some of the Friday Fun Day stuff. And the book talks about this as well. The reason I emphasized and wanted to make sure we touched upon it on Friday, this concept of pseudo instructions, is not because necessarily pseudo instructions are themselves this incredibly important topic. I don't think they necessarily are just by themselves. The reason I emphasized it on Friday and I'm bringing it back up here today is they make for a nice little quiz and exam questions. That's the honest truth. That those C to MIPS translation questions tend to be long, time-consuming questions because one line of C can very easily be many lines, multiple lines of MIPS programming. But these pseudo assembler type questions or pseudo instruction questions can be very straightforward, kind of one line to one other line or one line to two line type questions. They're the same concept. It's how do I take this functionality and translate it to MIPS? So it's covering the same big picture in the class. It's just easier to write, easier for you to answer, easier for me to grade those kind of questions. So we talked about this one on Friday. How would one potentially implement a move instruction? Um, a common type quiz question would be how would you implement a branch less than style question? And we had talked about that. That branch less than does not exist as a native instruction, but it is accepted by Mars assembler as a pseudo instruction. You would implement it via a set less than first, taking this as basically your condition flag for the less than comparison, and then convert that into, depending on where you want to branch, a branch not equal or a branch equal afterwards. That kind of question is pretty fair game for the exam, not because pseudo instructions are themselves so important, but just because they just are very easy to ask those kind of questions. Little one off translation questions. Okay, so some rejected exam questions. This one was rejected because I asked something very similar on the exam on Wednesday. So not really rejected, some recycled exam questions perhaps instead of rejected exam questions here. One thing I'd like us to maybe try is I could certainly go through every one of these questions and tell you every single one of the answers. I could, and that's fine. I'd like us to try today, and a word of warning that we're going to try this now, to break you out into small groups. Since we do have 100 folks here, so 99 students and myself. I'll break you into 33 groups right now, and let's start on this question. I like this question for a couple of reasons. Um, as a short answer question, not as a much must match the exact answer type question on Canvas, because it's got a little bit of ambiguity to it. That's one of the reasons I like this question. How far can L1 be away? Well, what does that mean? So you already have to resolve that ambiguity. Is what does it mean for something to be far away? What does distance mean in this context? Is an important starting consideration for this exam question. Second reason I like it is it does require that understanding of from assembly mnemonics and syntax down to ISA and representation of instructions. So there is something you have to know because you wouldn't want to be looking it up for the first time on the exam about a branch instruction. What is it about the branch instruction that allows us to start to answer that question? This is very similar to the homework 3 question, by the way, right? Um, and then finally putting it all together. Now, what I know about the instructions representation, what does that mean in terms of how far L1 can be away? And the reason I wouldn't want this to be a fill in the blank type question is there probably is one exact answer, but I would like to give a lot of partial credit for those who kind of understand it and maybe just are off by one or something like that. Um, so I'd like us to take let's take in this question. To be honest, I would time this at about a 2-minute question on the exam. So it's okay if today this is a 20-minute question for you, as you know, homework, and you're going to take time, you're going to go look in the book, you're going to go remember what this is all about. On the exam, it's not a test of what you can look up in a week, what you can negotiate with your TAs over the course of a week. It's what do you know? What can you defend at this point in the semester? So I'm going to break everyone out if I remember how to do that. And let's take that amount of time and see how far we can get on this question. You're going to be paired up with a couple strangers, so enjoy. And again, if you lose the screen when you're in the breakout room here, it's the branch instruction. It doesn't matter that it's branch not equal versus branch equal. How far can you branch is basically what the question is asking. Let's take 3 minutes and do our best on this question and meet a new friend while you're in a breakout room. All right, we're just filtering back into the main room here, so we'll just give it about 20 more seconds. Um, I'd like to hear from you. So, in terms of the implementation, and let's continue just to use the chat. I would love to hear from folks, but I don't have a good way of figuring out, um, how to best unmute people at the right time, and I'll keep looking into better solutions for that. There's a good clarifying question that someone asked there, so thank you, Nathaniel. Let's wait just a minute because there's a few more people who are showing up. And now we're back to assumptions. Now you could argue the point of an exam is to try to read my mind and interpret exactly what I had in mind and then work backwards from there. Um, it's a valid clarifying question on this exam. If as long as you were clear in how you answered it, it wouldn't matter to me. So the clarifying question is, how are you measuring distance? And I said that, how far can L1 be away? Are you measuring it in terms of bytes in an address range, or are you measuring it in terms of instructions? And to me, the answer can be either. I think it makes sense in terms of instructions, right? Isn't that what we ultimately would care about? How many instructions can we branch and how much distance to the branch target instruction can we have? And the only gotcha I would say would be you can wrap yourself in a bit of a pretzel if you overthink that part. So let's think about this question. And I don't think I have to write down notes with regards to this because there isn't a lot of math that you'd actually have to do for this. But so how far can it be away? And what's hidden inside this instruction, as we have it here, is that it's that I type instruction, right? That's the thing you would already need to know for Wednesday. You can't be looking it up and trying to remember how that works. It's an I type instruction. That means it's 16 bits for the immediate field that's being used to encode the immediate. In this case, the branch target offset is what's being encoded in those 16 bits. And the other, and it's assigned immediate. That would be the other thing to remember. So that allows you to jump either in a positive direction or in a negative direction. So to start with, if we have an n bit value in our 2's complement representation, that allows us to have a range of -2 to the n minus 1 to 2 to the n minus 1 minus 1, right? So in this case, from -2 to the 15 to 2 to the 15 minus 1 would be what could be encoded inside that 16-bit as a 2's complement representation. And that would give you a lot of partial credit. So if you wrote that, that's not quite correct, but that gives you a lot of partial credit for that question, that it's 16 bits. That's the range of what 16 bits allows us to represent. What we had covered earlier in the semester, and there's some architectural reasons for it, right? As we started to draw out our PC plus 4 logic, it made sense to then do the branch logic sort of after that PC plus 4. Later in the semester, it'll become even more clear why it happened to have been done that way. But in MIPS, that branch target offset is added to the PC plus 4 value. So we assume that a branch of 0 is actually branching to the next instruction, and then we're adding that 16-bit offset to what is that next instruction. So the clarifying question was asked is, well, are we talking bytes or are we talking in terms of instructions? All I described was in terms of instructions just now. So +1 instruction is the default, plus that offset, which is -2 to the 15 to 2 to the 15 minus 1. So if we add that together, we get -2 to the 15 plus 1 to 2 to the 15 would be the range that we could branch in terms of instructions. In terms of bytes, it would just be that value times 4, right? So that would be, -2 to the 17 plus 4 to 2 to the 17 is what you would get if you multiply that 4 to go from instructions to bytes. And yes, the last two significant bits, because it's word addressable, just like for our load words and store words, you'd wind up having this counter or this pointer into memory for our instructions that in MIPS always has the two least significant bits being 0. That winds up always being the case for that reason. Yep. So if we take a look at so it's -2 to the 15 plus 1 to 2 to the 15 because it's a 16-bit value. And if we look at the actual operation, and the MIPS green card tells you this, but boy, is it hard to interpret while you're in the middle of an exam and trying to understand the pseudocode they use to represent what the branch is doing. It actually, as we implement it, we would be concatenating that value with 2 zeros to turn it into a byte offset. So it's kind of a free multiply by 4. But that's just to interface with our byte addressable memory. In terms of instructions, we have that 16 bits of information that allows us to jump in that range of 16, 2 to the 15, negative 2 to the 15 to 2 to the 15 instructions at a time. So multiple parts there. You have to understand what is meant by far away, by branch target. You have to understand that it's I-type. So 16 bits is definitely some major aspect of your answer. That's the majority of the points I would say for this. And then you have to remember maybe back from 281, what does it mean to have a 16-bit signed constant? What does that mean in terms of our range? And finally, if this was a 5-point question, maybe one of those 5 points would be, oh yeah, and we get a free PC plus 4 as part of our calculation for MIPS, and that's a MIPS feature. So multiple aspects there to get a full credit for this. Um, that's why it's also a rejected question. That's hard to grade, right? Um, too many things could potentially go wrong for you to lose points on this one. That second question's rejected because it's really hard to lose points on that. How about this one? So we talk about why I like pseudo instructions. And for those who are still asking, why is it 2 to the 15 versus 2 to the 16? I'll just say for now, and you have to kind of look in the book and review that offline. Would be it's a signed value. So for an n-bit signed value, you get that range of negative 2 to the n minus 1 to 2 to the n minus 1, and that is that's just something that is kind of assumed as we're dealing with two's complement representation, but that's why it's one fewer than just the 16, because it allows you to go both negative for half your range and positive for half your range. So you lose that bit of range. That's one way to think about it. This is an example of this question 3 here of a pseudo instruction. And the question would be really, how do you translate this pseudo instruction to MIPS native assembly instructions? That would be the assumption here, how it would be phrased. This one's rejected, I guess, because it's there's really just a trick to it more than anything else, and it requires a couple steps, right? You have to first, and I would have to explain it in more detail. What is an ROL instruction? I can't just put that on there and not say exactly what it is. But so let's describe what that is right now. So if we have an ROL instruction, um, and what was it labeled as? ROL, was it 7? I didn't catch the amount. Let's go back to that then. Oh, just destination, source 1 and source 2. So it'd be more useful to have an exact example of that versus just a generic one, which is a slightly harder question. So rotate 1 with a destination of T1, a source of, let's say, T4, and an amount, let's say 7. That is in contrast or a direct comparison to an instruction that we know is already a native instruction, which would be like shift left logical. So if this is shift left logical, this is rotate left. So the shift left logical, if it had the same exact inputs, and yes, not to stress you out, if this was on an exam, I would have to explain, and I would have to also show you a version of this picture for this to be a fair exam question. We can talk about life not being fair. That's a different issue. Where if this is T4 is kind of our source, our input value here. For the shift, we know that means that there's this movement of the individual bits by that constant amount. Let's draw the result, which would be put in T1 here, where bits 31 down to 0 of the output would be the equivalent of that input shifted by that amount. So this would be, in this result, would be basically the original bit 24, the original bit 7, and then the results would all just be zeros. Gotta turn off that feature at some point. Right, so we've taken that result and we've shifted it to the left by 7. That's a shift left logical operator, right? Where we talked about how it's equivalent by multiplication of a power of 2, but that's not relevant for this question. That's our shift left logical operation. The difference then in a rotate would be, instead of shifting out those values and basically dropping them, if we have this again as our input value T4, whatever, that wasn't a good enough rectangle. When we now do that shifting, The result looks kind of similar in that we have those two blocks of the shifted amount, where this would now be, T4 of bit 24 down to 7. But then what's here would actually be the result that got originally shifted out. This would now be bits 31 down to 25 of T4. So instead of those values just being shifted out entirely, this chunk that is remaining gets rotated into the value itself. And yet, certainly for a pseudo instruction question, the question is only meaningful if I describe what the pseudo instruction is doing. So now I've taken more time than I would have wanted to allocate for the question itself on the exam to explain what this one is doing, but that's a rotate left operation. So it is effectively doing a shift left, right? It's shifting the value to the left by the same amount. It's just not dropping those bits that got shifted out. It's replacing the lower order bits with those bits that got shifted out. So again, in the shift example on the right here, those bits 25 up to 31 get removed entirely. These upper bits here get removed entirely, and then we insert in zeros where we don't have any starting information based on that shift to the left. The rotate does that same shift to the left, so bits 24 down to 7 are exactly the same as the shift left logical version of it. But now the lower order bits aren't 0. The lower order bits are replaced by the bits that got shifted out, and that's those bits 31 down to 25 for that example. That's and I didn't invent that. That's the idea of a rotate operation, and it's very useful for crypto and other things. That instead of just shifting things out and inserting zeros, we're rotating it around, and in this case, rotating it by 7. I think this question, if asked in the general form, is a little tricky, where our source would be maybe that 5-bit shift amount field in our R-type instructions. But for our purposes today, and let's not break into rooms for this one, if it's a constant amount, if I'm telling you the pseudo instruction is rotate T1, T4, 7, then what would the equivalent MIPS instructions be to give you the same functionality, to give you the same result, right? That's what it means to have the same functionality, that ultimately, the value in T1 should be this. And how do we do that using other MIPS instructions? And I would say by and large, the question has been asked, can we use pseudo instructions? People have asked that about homeworks. People have certainly asked that already about exams. Generally, that's very much fair game. To whatever instructions Mars will accept, I'm happy with you using, works well enough. If it's a question about translating, and the question says, translate this pseudo instruction to native MIPS assembly instructions, then the assumption is you shouldn't be using pseudo instructions in your answer. And so translate it down to actual MIPS opcode instructions. Again, it's kind of synthetic examples, but they're nice bite-sized one. I could have given the same exact question using C coding instead, where we do a rotate operator in C. But I think it'd be a much harder question to interpret and to read. Here it is, just kind of visually rotate to the left by 7. How do you implement that in MIPS? Let's take a moment and take a think about it. And I'm open for suggestions. And there's going to be definitely more than one possible answer to this question, because there's more than one way to do a rotate operation. Tyler's got it, although his answer is sufficiently obfuscated that if you don't already know the answer, you may not appreciate his answer. So continue to think about it for a minute. Just take about 30 seconds. So obviously, it took me a long time to explain this question. This visual probably is an easier way to explain it than trying to explain it in words. Um, this is another probably 3-minute question on the exam. It's not a great one because it's kind of a either you get the concept of rotate or you not, and this is not a class about doing rotations. That's not the big picture of this class, but it's certainly the type of question that I like to ask. Sounds great. For a couple of folks have got it. Let's just take another 15 seconds or so. And everyone can read the chat and see the answer, except on Wednesday you won't be able to. So think about it and see what you would be able to come up with. And that is a good starting point. So recognizing that the output of these two, the instruction we'd like to implement and an instruction we already know about, are actually really similar, right? Is a good starting point for understanding this question here. Um, in this case, 25 out of the 32 bits are already correct. So in terms of implementing this, we could actually start with that. And we talked about how there is that assembler temporary. I don't particularly care for this type of question if you use it or not. I mean, that's what it's for. So to expand pseudo instructions into multiple instructions, um, so be it, right? But that's what it's for. And if you don't use it, that's fine as well. We could also just reuse T1 because the idea is the value in T1 is what we care about at the end. But this is kind of cleaner, and this is the idiomatic way of doing it in MIPS. So by starting with that, we now have AT that has 25 out of the 32 bits that we're interested in. And as several people noticed, and I appreciate that here, the 7 bits that we actually want to get into least significant bits, well, rotating it to the left gives you the equivalent operation of shifting it all the way to the right by the 32 minus that amount. And that's exactly what was written there. So um, if this is a rotate to the left by 7, that should be the equivalent of, right, it's at 31 minus it, it's not 32. Shifting it to the right, because this is bit 6, by 25, which is 32 minus 7. So we would take that value and shift it to the right by 25. Any mistakes made by me here are intentional, and you're supposed to check me on them and let me know that I've made a mistake. That takes this input again, gets rid of all the other bits, and only has now as the least significant bits those 7 corresponding to the upper 7 bits of that value. So now we have kind of 2 temporary registers, both of which have part of the answer, and as suggested, we could just OR those values together. And this time we do care about the result. This would be a correctness issue, where we do want the result to be, in this case, put into T1, because that's what the question's asking. Inputs T4, or that's the source register. The destination register is T1. We would want our destination register also to be T1. Someone asked, could this have been an add instead of an OR? Yeah, it'd be just fine. We talk about, and we will talk about more about the performance of addition, the critical path of an adder versus the critical path of an OR operator. It doesn't really impact the performance of our code at all, because those performance considerations are kind of baked into the performance of the processor, the clock frequency of the processor as a whole. So in theory, one is slower than the other. In practice, they'd be both the same exact speed, and it would be fine either way. Or to me makes, no pun intended, the most logical sense for this type of operation. We have 2 parts. We need to kind of glue them together like this. The OR operation makes a lot of sense. That'd be a good 3-minute question, on the exam. That'd be my thought. It took us longer than 3 minutes to explain the question, but from this pseudo instruction that does something kind of arbitrary, and it's my job to explain that functionality as clearly as possible, certainly on an exam with time limits. What does that correspond to in terms of MIPS assembly? This is testing a couple of things. It's certainly testing in a way that's hard to otherwise get a hold of your understanding of what's happening with MIPS, what instructions we understand in MIPS, and what do they do. It'd be very hard to reason about this from base principles without taking a couple days otherwise, and you won't have that on the exam. So the question about, for this one with a 7, you don't actually need to store that 7 anywhere. By the way, Sam, that's a very good question. But that 7 doesn't need to be stored anywhere for the pseudo assembler expansions, because that shift amount is already a constant baked into the instruction, right? There is no, not that we're supporting, there is no shift left logical variable instruction or shift left logical register instruction. It's shift left logical with this constant. And so because it's a constant, the assembler should be able to recognize that because you wrote 7 here, it can do the math as the assembler itself and recognize that we need a 25 here, and can also hard code that value. So that does matter. That it can recognize this. We don't have to actually bit shift the instruction itself and figure out where that 7 is stored and all that. We don't have to do any of that to support this pseudo assembly expansion here. And someone also asked about the order of these two instructions, and that would also be fine. Those two shifts could be done in either order. I don't think it matters. You do need a temporary register for this to work, though, right? Because we have to store two temporary values to get this to work. So having that AT is very useful here. How are we doing for time? Let's see if we can do one more. That one's no good. I don't like that one. That one's okay. I like this one. And I like this one because, well, you can't see what I'm looking at. Because let's see here. This last one, because it's something that we've been doing a decent amount of already this semester, and I think it is so far one of our big. So it's question 7 here. Question 5 is also fine. Question 6, I don't like to ask those kind of things because it's too generic and fuzzy. And if this was a homework question, I'd be spending lots of time in office hours trying to decode what I meant when with people. But 7's a good question. So given what we know about how we've designed the processor to date, and when I say that, we haven't officially been covering that section of the textbook yet. So it's still pretty much a fair game question, though, because we have been doing this quite a bit, right? So I would say this is our understanding of the processor to date. Where we've been in terms of building out the R type and the I type instructions, a little bit of what's happening with the branch and all that as well, but certainly a little bit of understanding PC plus 4 and how that operates. This is a big chunk of your project part B that you're going to be getting to in about 4 weeks here now. But so when I say that, based on our understanding of the processor's data path and control it is discussed in lecture, come up with a scheme to add the load upper immediate instruction to it. I think it's a good question. Um, no one knows the answer, I think, coming into the exam, right? You'd have had no reason yet at this point in the semester to have thought about that. So this is asking you, do you understand the concept of what we've been doing so far? Which this will tell me a lot about if I've been effective or not so far this semester. What does it mean to add a new instruction? I've seen a little bit of that challenge, right? As we've gone from lab 3 to lab 4, I've definitely seen a little bit of that challenge of what does it mean to add these loads and stores to our existing data path, which is all what lab 3 and lab 4 were doing, right? Or lab 4 was doing. And the philosophy, at least the 381 philosophy, I jokingly have called it, add a mux, but that has been the philosophy, which is support the instructions that you already have, and support the instructions that you already have, and consider what new data path elements are needed for this additional new instruction. For load word and store word, it's this whole data memory, and there's a lot going on with regards to that. And this data path doesn't show your lab 4 data path at all. There's no data memory in this one. We could add it. That's a different exercise we'll do later in the semester. But for this load upper immediate instruction, well, now we go back to the question. Now you have 2 tasks. Now you have the green card in front of you, and you're asking, well, what the heck is load upper immediate? And well, it's an I type instruction. So it has very similar syntax to the other the other ALU I type instructions. Load upper immediate, destination register, some source register. Careful. I should have the green card handy on me as well. Load upper immediate into this register some 16-bit constant. This question is not on the exam, so it's okay if I muff it a little bit here. That's fine. Load upper immediate, a 16-bit constant. into the upper half of the register. So the result of T2 afterwards is exactly this, and no else. Afterwards, it's this value that's our 16-bit constant with nothing, or zeros, I guess, in the lower 16 bits of that register. That's load up or immediate. And in fact, it is a good question. I guess it's too late for me to put it on there now. There's a lot of different ways you can implement it with this existing data path understanding. Now, on a Canvas exam, certainly for this first exam of the semester, there's no opportunity for you to be drawing your thoughts and to draw it out visually. And to the extent that's a disadvantage for some versus others, we'll see. And I feel for you, but I don't know exactly who that disadvantages or advantages that you can't draw and instead just have to describe in words how you would do such a thing. I'd like us to take, and we got 2 minutes here, break out one more time. I know some of you have already got it. Let's break out one more time. And you'll be potentially with somebody else this time. Make it interesting. And how you would implement the load up or immediate. Okay, you should have been invited to join. Kind of hate these breakout rooms. We'll make the most of them. Welcome back. I know we're running a little low on time. I will take no more than 1 minute once everyone gets back in here. Um, I'm always trying to be cognizant of the time and those of you who have to get to your next class uh, that could be on campus. But let's just take 1 more minute once people have filtered back in. But any thoughts on how you would implement this? Um, Lots of possibilities. And so that's in that sense, it's a good exam question because lots of ways to get full credit. In lots of ways, that's a bad exam question because I have to actually sit and read every answer and think about whether it's correct or not. I like that one. I would consider that the first approach. It's not exactly shift left logical, but I would call it, treat this as a shift left logical, like immediate instruction, right? And we can talk about what that means, right? We know that this is equivalent to shifting to the left by 16, but it's a little different than a regular shift left logical by 16 because that's taking a register's input, whereas this is taking an immediate as input and shifting that to the left by 16. But you could certainly implement this such that you have an additional mux into your shifter, and it's taking the immediate input versus taking the register value input. And otherwise, it operates exactly like a shift left logical instruction. I think anything that mentions this on the exam for this question, if there was a checkbox I could hit, check, move on. Good, you got the idea. Um, Absolutely. So it would be 16, not 8. That's an important consideration to think about. So I would say anyone who puts shift left logical immediate 16 in there would be in good shape to get that check mark. The other approach is, and you would have to add a little bit more detail than that, would be, and that is absolutely correct as well. And as you're working on your projects, as you're building the single cycle processor, um, you're going to have those little mini design decisions, and about 30 of them throughout that time of designing that processor, which is, do I try to implement this additional instruction as a special case of existing instructions, or do I treat it as another one-off and add another muck specifically for this case? And in this case, that either one is perfectly fine. That would certainly be one approach for it, which would be, I have this constant. So to be more specific, it's not just add a mux, is, you know, concatenate the 16 bits of zeros, right? To get your 32-bit constant. It's a little bit different than our sign extender and zero extenders we were talking about for lab number 4. And mux the register write data, right? Whatever you want to call that port. With some signal called is load upper immediate instruction that is only high when that is the instruction that is currently being executed. That'll absolutely work. That path gets used only in the case of this being the instruction that's executed, and is dormant the rest of the time, doesn't really affect anything the rest of the time. Either approach is perfectly valid. You can't just say add a mux. That's true, but not sufficient. But add a specific mux to do something specific is what you would need to do. Let's leave things here for today. I'm seeing some questions about whether the shifting would work properly for this purpose, and it would. There is nothing we actually have to preserve if we look at what the output register needs to be here. We're not shifting T2. We'd be shifting this constant, and so shifting that immediate value versus the T2 register, and then just storing it back into the register file. Let's leave things here for today. Um, I've got my office hours today, although the timing probably isn't perfect for you to ask exam type questions outside of process questions. Otherwise, between now and roughly 47 hours from now, do post questions on Discord. Any homework question that has been graded already, any exam practice question that you're unclear on, either my phrasing or what you think the answer should be. Let's use the general channel for that. We should get some good discussions there. Um, there's a lot at stake in some sense, right? It's just an exam. There's a couple others. I want everyone to do extremely well in the exam. Please prepare for it, and I think you'll have an okay time on Wednesday. Sort of looking forward to it. I'll see everyone on Wednesday. Enjoy.